Okay, so Mekhala is going to talk about tiling strategies for spotlight. As we just heard, there are going to be multiple beams and these beams have to be tiled. And Mekhala has done some work on tiling these beams and she's going to talk about that.
I'm Mekhala and I'm engineer at GMRT. So I'll be talking on this optimal tiling of spotlight field of view with multi-beam synthesis. So you have seen this diagram and I'll be focusing on this block basically, the beam tiling block. Since throughout this workshop, we have been hearing about the FRBs, but just to have a connection with the topic, I'll just give a brief on what are FRBs. So the FRBs are highly energetic transients lasting for a few milliseconds. They are from the extragalactic, sources, and high luminosity makes them detectable across the vast distance. And the types in which they are found are non-repeaters and repeaters. And the astronomers or scientists across the world, they are studying these astrophysical, high energy astrophysical processes behind them. But the study is still not fully understood. And the reason being, or the major challenge which they are facing in studying FRBs is its accurate localization. So to address this, to have the accurate localization, what can be the parameters is like one can have a very high spatial resolution, which can be achieved through interferometric array. And till now, study or discoveries, we have found that the FRBs are mostly lasting in the range of 110 megahertz, going up to 8 gigahertz for the repeaters. And for non-repeater FRBs, they are ranging from 350 megahertz to 1.53 gigahertz. So if you see these two parameters in respect of GMRT, so GMRT is actually satisfying all these two needs, that it is an interferometric array. At the same time, the frequency range are falling well within the operable range of GMRT. Now, the second thing is like we need to, when we address the spatial resolution, the other parameter which is there is to increase your survey speed. And to do that, we can form multiple beams. And that is being addressed by the spotlight. So spotlight is enhancing GMRT's capabilities by forming multiple beams. So, yeah, now coming to the real, this beam tiling topic. So we have developed a multi-beam simulation package. So why is there the need to develop this package? First thing is like we have to optimally cover the field of view, optimally place the beams. And in order to do that, we should know the exact beam shape or near about approximate beam shape so that we can cover the full field of view and we can increase our survey speed. The second thing is every time as you observe the source from rise to start, the beam shape is changing. So in order to address that, one need to have the dynamic beam estimation capability. And this will then, with this, we can have the first level localization with individual beam across the field of view. So this package actually grids the beam across your field of view. And since Spotlight is in commensal, is running in commensal mode, so this package actually provides the feature to work in an unsupervised manner. It generates 2000 post-correlated beams, and the tiling pattern is updated anywhere from 1 minute to the scan boundary. Currently, we have kept it for the scan boundary. So going through how the simulation package works, you can see that here it shows the tool flow. flow of the estimation, where in order to get the beam estimation, we need few parameters on which it is dependent. The first being the frequency on which you're observing. The other is the source location, the array deck, or the pointing source, you can say. Then the date and time of observation and array configuration. So based on these 4 parameters, we are estimating the beam shape. So when we estimate the beam shape, we are providing 3 different options. Either we can go for an Gaussian fit on the central part of the beam, or you can have the elliptical fit over the contours, or in case of a fail-safe option, since we have simulated multiple test cases, but since if we miss out any one and if it doesn't fit, we are providing the fail-safe option of providing the UV plane distribution as a fallback option on it. And once you have the beam estimation ready, that is the major axis, minor axis, position angle of it, we are forming 2000 such beams. So for commensal mode, we are going with forming 2000 beams in order to cover the broader field of view. But for other modes, where the user is more interested in some targeted science, it will give their field of view, and depending upon the field of view, it will form the number of beams. So these 2000 beams are actually given to the correlator, which Harshvardhan has just now talked, on which he is forming the beams. So these are some features of the package. Apart from forming the post-correlated beam, it is also giving the facility to generate the phased array beam also. And the user can have the option to fit the beams at his overlap ratio, whatever he wished to go for. And then while tiling, there is option, like in tiling, sometimes it happens that the pointing center does not come into the center of one beam. So there is a feature where we can recenter the tiling grid to pointing center. Also, it gives a prior estimate of field of view at different isofocal levels for both the fits. Then there are various other features which user can play around, like it can change the image size, the pixel size of the image, number of pixels, and it is saving the intermediate files which contains the information about the beam estimation, the observation setup, and the tiling pattern generated by it. Also, we can, using these intermediate files, we can go back and replot the PSF or tiling pattern. So execution time, if you see execution wise, the program takes almost around 30 seconds. Yes, so now since we have developed this package or the simulation program, but to validate the results coming from it, we have compared the results from CASA PSF with the one generated by this simulation program. So here you can see the structure from CASA PSF with the post correlation beamform is like kind of matching. Apart from this, we have simulated it for different times. So that keeps the, that confirms that your position angle or the way the beam is changing over time, that is matching. So yeah, as you know, the spotlight is actually formed on post-correlated beam. The advantage here, you can see the traditional phased array beam are more wider because it contains the autocorrelated part in it, whereas the post-correlation correlated beam are optimum in size since they don't have the autocorrelated part. And since we are observing the signal over a wide bandwidth, but the estimation of this beam shape is done on center frequency, and we have done it for different bands and observed that the if we go for a central frequency beam shape estimation, we don't find much change in the beam shape over the frequency range or over that bandwidth. So the different modes which is offered by Spotlight are commensal, targeted, and multi-source mode. So in commensal mode, we are using moderate baselines, typically central square with nearby arm antennas, counting to 22 antennas, and it generates 2000 beams from it, covering a wider field of view comparable to the primary beam width. Then the next mode is targeted mode. It is using the full GMRT array, thereby increasing the sensitivity. And in this mode, we are generating anywhere between 24 to 240 beams for the given field of view. Here, the field of view is smaller, and it is mostly for the targeted science, like globular cluster. The next third mode is multi-source mode. It is slightly extended version of the targeted mode, where the user can observe different sources in a given field of view. And it is useful in studying pulsar timing. So we have developed a web tool for this package, and it is mostly for the targeted mode and multi-source mode, where the user gets the facility to play around and get a prior estimation of the beam shape, the number of beams, and the field of view it is covering. So user can trade off between the number of beams or between the sensitivity, and can go for the desired field of view with it. And it helps in visualizing the multi-source mode also. Tiling pattern for the multi-source mode. So these are some pictures from the web tool. So here you can find that we have to give all the input parameters like the array configuration, the array and deck frequency, center frequency on which we are observing, the date and time of observation. And once you give this input, it generates different, some information or gives the estimate of the beam in the form of major and minor axis along with the position angle and the field of view it is covering for given number of beams. So with this, the user can play. If the field of view for 160 beam is more, it can go back and change the sensitivity or reduce the number of beams and so on. And finally, after selecting one such option, we can tile the beam. And these are the results where we have actually taken the source off axis, and we have compared the SNR plot of generated from the simulated program with the folded pulsar SNR map. To summarize, the package is a useful tool for gridding n number 2000 beams across your field of view in an unsupervised manner, and tiling pattern can be updated as fast as at 1 minute rate, but currently we have kept it for a scan boundary update. And the three different modes which it is offering are commensal, targeted, and multi-source mode. And we have developed the tool for the users who can go and get a view of the field of view for targeted and multi-source mode. That's all. Thank you.
Questions for Mekhala?
Thanks for the great talk. A bit of a naive question. When you're talking about the targeted mode, are you also, so you mentioned that you could recenter the beams so that the target is at the pointing centroid is at the beam center. But does this mean when you're, can you also track the object like this in that manner where the target location is always at the beam center?
Yeah, we can do that. We can recenter it. Actually, it is the part of tiling your beams and number of beams. So in that process, sometimes it happens that your one beam doesn't contain the center as the pointing center. Mm-hmm. But there is option. And for commensal mode, we are ensuring that we are tiling one beam at the pointing center.
Okay, so but that's like a one-time operation, or is it something that you could track in real time? So
Yeah, we are tracking.
Right. Okay.
It's dynamic beam estimation. So every time at the scan boundary, estimating the beam shape, we are forming new tiling patterns.
Okay.
That way.
Thank you.
Prabhu? Mekhala, there is a small question. Maybe you addressed it. The beam overlaps at what power level? Slide, yeah. What is the slide 30? Yeah, slide. Any slide is okay.
Here?
No, between, yeah. At what power level they overlap, or you can position it anywhere?
Option for commensal mode, we have kept it at half power, but we are giving the option where the users can trade off between the number of beams and overlap they are choosing.
Okay, I think it's like
so the level goes from 0.3 to 0.9.
Slide 13, you are showing something with time. It's not clear why the power was dropping.
Where?
13, I think.
13.
Yeah.
Oh, it's not the power. It's
the
the
half
power beam width. Yeah. So we have just, since we are working at, we are estimating at the center frequency, whereas if we are observing at over the bandwidth, so we just want to ensure that there is no much trade-off by choosing center frequency. I mean, it's a good thing to go for center frequency.
Sorry, as time goes by, why is it dropping?
Yeah, that might be because we have the time 0 is the rise time of the source, where your bandwidth is, source is at horizon
so
and bandwidth is higher.
Thank you. Okay, so in the interest of time, we'll move and thank Mekhala.